The James Webb Telescope, the JWST, has done it again. It has found a galaxy so old it's beginning to rewrite the rules. With this discovery, a lot of things are about to change. To understand why, let's rewind. Not to the dawn of time, but to 2022. Up until 2022, the most distant galaxy we'd ever seen was GNZ11, spotted by the Hubble Space Telescope. It was a landmark discovery. Hubble, with its 2.4-meter mirror and incredible optics, had taken us deep into space. But there was a limit to how far it could see. Then the James Webb Space Telescope was launched. Armed with a massive 6.5-meter mirror and tuned to infrared, the exact kind of stretched ancient light that early galaxies emit, Webb didn't just continue Hubble's work, it crushed its records. In one of JWST's early campaigns, a galaxy named JADESGSZ130 was found. It held the record for the most distant confirmed galaxy with a redshift of 14.32. Redshift, in a nutshell, is how much the light from a galaxy has been stretched by the expansion of the universe. The higher the redshift, the older the light. Then came MAMZ14, with a redshift of 14.44. It pushed our view even deeper into time. And it wasn't just the redshift that stunned scientists, it was what the galaxy actually looked like. This galaxy is tiny, about 500 light-years wide. For comparison, our Milky Way spans over 100,000 light-years. But MAMZ14 is also incredibly bright. Normally, galaxies this early in the universe should be faint and hard to detect. Not this one. MAMZ14 is bursting with newborn stars, a rapid-fire stellar nursery in the first few chapters of cosmic history. But one feature, or rather the absence of one, made it even stranger. There's no sign of a supermassive black hole. Most of the galaxies we've studied with intense star formation host a supermassive black hole at their center. These black holes are thought to play a key role in galaxy evolution, regulating star birth, shaping structure, and driving growth. But MAMZ14 doesn't have one. The mysteries don't stop there. When astronomers used JWST's spectrograph to analyze the galaxy's light, they found it rich in nitrogen. Unusually rich. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that MAMZ14 is forming stars in extremely dense environments. That's not what we expected. Galaxies this early in the universe should be chemically simple, mostly hydrogen and helium. But MAMZ14 is telling us that multiple generations of stars had already lived and died before it. That means galaxy evolution may have started much earlier than we thought, and it raises a big question. How many more galaxies like MAMZ14 are out there? Before JWST, we thought galaxies this early would be incredibly rare, but now we've found more than we ever expected. These ancient bright galaxies, sometimes called little red dots, are popping up across JWST's surveys. Astronomers now believe that MAMZ14 may be the record holder as of now, but it might not be for long. And that's where things get really exciting. The more we look, the more we find. And every discovery chips away at our assumptions. If galaxies like MAMZ14 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? Does this challenge our cosmological models? In a word, yes. Our current understanding of galaxy formation says that these kinds of galaxies should be rare, slow-growing, and simple. MAMZ-14 is none of those things. It's fast, bright, and chemically complex. It's not that our models are wrong, but they are incomplete. MAMZ-14 is a clue that the early universe might have been far more active than we imagined, and this is just the beginning. Later this decade, the Nancy Grace Roman Space Telescope will join JWST in scanning the early universe. Roman will cover much larger areas of sky with incredible detail. Together, these telescopes could uncover hundreds, maybe thousands of galaxies like MAMZ-14. Each one a time capsule from an era we're only beginning to understand. But for now, MAMZ-14 stands as a milestone, a flicker of light from when the universe was still finding its footing. And the more we probe JWST's findings, the more the universe defies expectations. Some scientists interpreting the data have proposed something bold, that our entire universe might exist inside a black hole. New research has uncovered an intriguing mystery. The majority of galaxies appear to be rotating in the same direction. The lines formed by the peaks here allow us to identify the direction of the curve of the arms of the galaxies, and consequently their spin direction. This is significant. In a truly random universe, galaxy rotation should be roughly evenly split between two directions. According to the study's authors, this unexpected finding, which contradicts existing cosmological models, may hint that our universe itself is inside a black hole. To understand this, we need to look at the physics of black holes. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Anything that crosses this boundary is forever lost to an outside observer. However, what happens inside the event horizon is still a mystery. This is where black hole cosmology comes in. Also known as Schwarzschild cosmology, it suggests that our observable universe might actually be the interior of a black hole within a larger parent universe. Now consider the Big Bang. The standard model tells us the universe began as a singularity, a point of infinite density, just like the center of a black hole. If our universe is the interior of a black hole that formed in a larger parent universe, then the Big Bang wasn't an explosion in empty space. It was the collapse of matter into a black hole, creating a new universe inside. This has another implication. Each and every black hole in our universe could be the doorway to another baby universe. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce. Scientists believe this idea could explain several cosmic mysteries. For example, black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Another factor could be torsion. In extended theories of general relativity, such as Einstein-Cartan theory, torsion is a property that accounts for the intrinsic spin of particles and can influence space-time curvature. Some theories suggest that torsion could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward, potentially giving rise to a new universe inside. Scientists say this rapid recoil after such a bounce could be what led to our expanding universe, an event we now call the Big Bang. Instead of an explosion from nothing, it could have been a rebirth, from the core of a black hole in a parent universe. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing, self-replicating process. Another intriguing possibility is that the universe may have a preferred axis. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. If the universe does have a preferred direction, it could point to unknown physics, possibly related to how our universe formed inside a black hole, or how fundamental forces interact on the largest scales. Moreover, the existence of ancient massive galaxies so soon after the Big Bang challenges our understanding of cosmic evolution. But while the universe inside a black hole theory is tantalizing, there could also be a simpler explanation. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. In any case, the universe is turning out to be far stranger than we ever imagined. There's a star in our galaxy, spinning faster than a jet engine, denser than a mountain crushed into a teacup. It doesn't shine the brightest. It doesn't sit quietly in the night sky. This one is different. It's unstable, on the edge, and it could collapse at any moment. No. This one is different. It's unstable, on the edge, and it could collapse at any moment. But here's the twist. It's not some remote cosmic phantom. It's in our galaxy, right now. Part 1. The star that shouldn't exist when a massive star dies, it doesn't go quietly. It burns every last atom of fuel, struggling to hold off the one force that always wins, gravity. And when gravity does win, the core collapses. The outer layers explode in a supernova. What's left behind? Something small, something impossibly heavy. A neutron star. A corpse, yes, but one unlike anything else in the universe. Imagine stuffing all the mass of the sun into a ball just 12 miles wide. If you could somehow scoop up a teaspoon of this material, it would weigh more than Mount Everest. And that's not exaggeration. That's physics. Part 2. Meet the pulsar. Some of these dead stars don't just sit still, they spin. Fast. Really fast. So fast, in fact, that they sweep beams of radiation across the galaxy like a cosmic lighthouse. These are called pulsars. In 1967, the first pulsar was detected. The pulses were so regular, so precise, that some scientists thought it might be aliens. They weren't wrong to wonder. It was something truly alien to our understanding. These pulsars can spin hundreds of times per second, and they don't slow down easily. For millions of years, they spin, beam, and burn on. But there's a darker kind, a predator among stars. Part 3. The Black Widow. Some pulsars don't live alone. They steal. Nearby stars get caught in their gravitational grip. The pulsar tears away at its companion, atom by atom, feeding off its matter, spinning faster, growing heavier. Scientists call these Black Widow pulsars because, just like the spider, they devour their partner. And here's the danger. Every stolen atom is one step closer to disaster. There's a limit to how much mass a neutron star can hold before it collapses into a black hole. Part 4. PSRJ 0952-0607. The Star on the Edge. One of these monsters lives closer than you think. It's called PSRJ 0952-0607. Not a flashy name. No sci-fi fame. but its stats read like a cosmic death sentence. It spins at 707 revolutions per second. That's not a typo. Every second it completes over 700 full spins. And it's heavy. 2.4 times the mass of our sun compressed into a city-sized ball. That should be impossible, and yet it exists. Barely. Its companion, a fading white dwarf, still orbits, still feeds it, still pushes it closer. To the edge. Part 5. What happens if it collapses? If it crosses the line, if it takes in just a little more mass, this spinning time bomb will collapse into a black hole. But there will be no explosion, no flash, no warning. One moment, pulses. The next, silence. Just like that, a black hole is born. And if it happens to launch relativistic jets, narrow beams of radiation traveling near light speed, and if those jets are aimed at Earth, we could be in trouble. Gamma-ray bursts this powerful have been suspected of causing mass extinctions before. Part 6. The magnetic monsters. Magnetars. But pulsars aren't the only threat. There's a stranger breed, magnetars. Their magnetic fields are so powerful they could tear your atoms apart. In 2004, one such magnetar let off a gamma burst so strong it overwhelmed satellites. From 42,000 light-years away. If it were just 10 light-years closer, Earth would have been toast, and they don't wait quietly. They can quake, unleashing more energy in a second than the sun does in 100,000 years. Part 7. What if one got close? Let's say one drifted close, maybe not to Earth, but just into our solar system. The gravity would warp planetary orbits. The radiation would sterilize the surface. If it were a magnetar, it could rip your body apart without touching you. Eventually, it might even collapse into a black hole. Right here. Part 8. But should we worry? So should we be worried? Number, not really. These stars are real, and yes, they're dangerous, but space is big, really big. PSRJ 0952-0607 is 14,000 light-years away. Even if it collapsed today, the effects wouldn't reach us for 14,000 years. But they matter. Because they show us the edge of what's possible. They remind us that the universe is not built for comfort. It's built on gravity, collapse, pressure, and spin. Part 9. Final thoughts. We orbit a quiet star. We live on a calm planet. We breathe air untouched by cosmic radiation. But out there, scattered across the galaxy, are stars spinning themselves apart, collapsing into darkness, bursting with magnetism and gamma fire. They are deadly. They are beautiful. And they are a reminder. The universe doesn't care about comfort. It only cares about what happens when matter meets force and runs out of time. The universe isn't real to us. On October 4th, 2022, John Clauser, Alain Aspect, and Anton Zeilinger were awarded the Nobel Prize in Physics for a discovery that challenges one of our most basic assumptions. That the universe is locally real. In other words, they helped prove that, at the quantum level, reality doesn't exist in a definite state until it's measured, and things far apart can still instantly affect each other. And what makes this even more remarkable? They effectively proved Einstein wrong. What does locally real mean? It's two ideas combined. Locality. Things are only influenced by their immediate surroundings. Information or influence cannot travel faster than light. Realism. Objects exist with definite properties, independent of whether or not someone observes or measures them. Einstein strongly believed both were true. If a tree falls in a forest, it does make a sound, even if no one's there. But quantum mechanics, as championed by Niels Bohr, suggested otherwise, that particles exist in a superposition of possible states until measured. Einstein's thought experiment, the EPR paper. In 1935, Einstein, Podolsky, and Rosen proposed a thought experiment, now called the EPR paradox, involving entangled particles. Two particles created together in such a way that measuring one tells you something about the other, no matter how far apart they are. If one particle is found spinning clockwise, the other must be spinning counterclockwise. But quantum mechanics says they don't decide on a spin until they're measured. So how does the second particle know what to be? Instantly. Einstein hated this. He called it spooky action at a distance and insisted there must be hidden variables, unknown factors that determine outcomes in advance. He believed quantum mechanics was incomplete. For decades, this debate sat in limbo, until John Bell came along. Enter Bell's theorem. In 1964, physicist John Bell devised a way to test this dilemma experimentally through what's now called Bell's theorem. It created a mathematical boundary, a set of conditions, Bell's inequalities that would hold true if hidden variables existed and reality was locally real. Break the boundary, then quantum mechanics wins. The experiments begin. John Clauser's test. In 1972, John Clauser performed the first real-world test of Bell's inequality using entangled photons and polarizers. By measuring how often two distant detectors agreed or disagreed on the polarization of light from entangled particles, Clauser could determine if the results fit with hidden variable theories or quantum mechanics. The result? Quantum mechanics won. The universe failed the local realism test. A possibly true story says Clauser ran to tell Richard Feynman, who promptly threw him out of his office, saying, "Good. Now get on with some real physics." Aspect and Zeilinger closed the loopholes. Later, Alain Aspect and Anton Zeilinger refined these experiments, closing loopholes that skeptics pointed to. Aspect improved the experimental timing, ruling out hidden communication between particles. Zeilinger showed that entanglement could even be transferred between particles, a process now called quantum teleportation. Why it matters. This isn't just philosophical, it's the foundation of quantum computing and quantum encryption, which could one day surpass anything classical computers can do. Because quantum particles don't just store information. They share it in ways classical physics can't explain. Still, it's important to note, we can't use entanglement to send messages faster than light. The process is random at its core. So while it looks like faster-than-light communication, you can't control it. So no violating Einstein's speed limit just yet. The takeaway: Einstein was one of the greatest minds in history. But in this case, the universe turned out to be even stranger than he imagined. At the quantum level, reality doesn't exist until observed, and entangled particles seem to defy the very structure of space and time. And this is only the beginning. The dark matter map that's changing everything. Imagine a vast cosmic spiderweb stretching across the universe. Invisible to the human eye, but holding everything in place. Galaxies, stars, planets, even us. All tied together by something we can't see, something we call dark matter. For decades, scientists have known it's there. We can measure its effects. We can see how galaxies move too fast to be held together by visible matter alone. But we've never actually seen dark matter itself. That is, until now. In a stunning breakthrough, astronomers have created the largest ever 3D map of dark matter, revealing a hidden structure behind the universe we thought we knew. And what they've found might change everything. What is dark matter? Let's start with the basics. Dark matter is invisible. It doesn't emit light, reflect it, or absorb it. We can't see it with any telescope, but we know it's there because of its gravitational pull. Think of it like wind. You can't see wind itself, but you can see the trees sway. You can feel it press against your face. That's how dark matter behaves. It shapes galaxies, it bends light, it warps the structure of space. In fact, dark matter makes up about 85% of all matter in the universe. Everything we've ever touched, built, or studied, and all the stars and planets, that's just the remaining 15%. So how do you make a map of something that's literally invisible? The answer is gravitational lensing. When light from a distant galaxy passes through a region filled with dark matter, the gravity from that dark matter bends the light. It's like looking at an image through a warped piece of glass. This distortion, called weak lensing, is extremely subtle, but with enough data, you can use it to trace where the dark matter must be. By collecting millions of galaxy images and analyzing how their light is distorted, astronomers can build a map of dark matter, not by seeing it directly, but by studying its fingerprints on light. And now, using a survey called DES, the Dark Energy Survey, scientists have used this technique to create a full 3D map of dark matter spread across billions of light years. It's the most detailed picture of the dark side of the cosmos ever made. What the map shows is astonishing. Instead of being evenly spread out, dark matter forms a cosmic web, long filaments stretching across the universe, connecting clusters of galaxies like beads on a string. These filaments intersect at dense nodes, regions where thousands of galaxies are crammed together. These aren't random shapes. The web-like pattern is exactly what simulations predicted, and it confirms that the large-scale structure of the universe is governed by dark matter. This cosmic scaffolding determines where galaxies form, how they cluster, and even how they evolve. Without dark matter, galaxies wouldn't exist at all. The web holds everything together. But here's where things get weird. When scientists compared the actual map to the predictions of our standard cosmological model, the Lambda cold dark matter model, they found a subtle mismatch. The real universe seems to be less clumpy than expected. The dark matter is there, but it's not clustering as tightly as the simulations say it should. This might seem like a small issue, but it could point to a fundamental flaw in our understanding of the universe. Maybe dark matter behaves differently than we thought. Maybe we're missing something about dark energy. And this is the big one, maybe Einstein's theory of gravity needs to be revised on cosmic scales. It's a mystery, and it's growing more serious with every new survey. Mapping dark matter isn't just about solving a cosmic puzzle. It's about understanding the invisible engine of the universe. Dark matter drives galaxy formation. It influences the expansion of space. It may even hold clues about the true nature of reality. If we can figure out what dark matter really is, whether it's a new kind of particle, a quantum field, or something even stranger, it could unlock an entirely new era of physics. And with new telescopes like the Vera C. Rubin Observatory and the Euclid Space Telescope, even more detailed maps are on the way. We've mapped continents. We've mapped the ocean floor. We've mapped the surface of Mars, but now we're mapping the unseen. The 3D dark matter map is a snapshot of the invisible forces shaping our universe, a reminder that the universe is far more than meets the eye, and that the biggest discoveries often lie in the shadows. The invisible web is real, and we've only just begun to trace its threads. Bizarre weather on distant worlds. Imagine looking up into the sky and watching glass rain fall sideways in a 5,000-mile-per-hour wind, or watching metal clouds form in a red, stormy atmosphere, so hot they evaporate into vapor. It sounds like science fiction, but it's not. Thanks to a new wave of exoplanet discoveries and a giant leap in telescope technology, we are now beginning to glimpse the weather on other worlds. And what we're seeing is nothing like Earth. These are the wild, unpredictable, and often terrifying alien storms, and they're revealing just how strange and extreme the universe really is, peeking into exoplanet atmospheres. Let's rewind a little. For years, astronomers have been discovering planets outside our solar system, what we call exoplanets. Thousands have been found so far, ranging from massive hot Jupiters to rocky Earth-like planets. But detecting a planet is one thing. Studying its atmosphere, from light years away, is another. That's where the James Webb Space Telescope and other powerful observatories come in. Using a technique called transit spectroscopy, scientists can examine the starlight that passes through a planet's atmosphere as it crosses in front of its star. Molecules in the air absorb specific wavelengths of light, leaving behind a unique fingerprint. And those fingerprints are telling us something wild. Many of these planets have weather systems that defy imagination. One of the most famous extreme exoplanets is HD 189733b, a gas giant about 64 light-years away. It's similar in size to Jupiter, but the similarities end there. This planet orbits so close to its star that its atmosphere is heated to over 1,700 degrees Fahrenheit, 930 degrees Celsius. Winds scream across its surface at 5,400 miles per hour, and its clouds are filled with silicate particles, yes, tiny pieces of glass. When storms form, glass rain whips through the air, driven sideways by super hurricane winds. If you were standing on this world, as you wouldn't be for long, you'd be shredded by molten glass flying faster than a fighter jet. That's not a storm. That's an apocalypse. Then there's WASP-76b, another ultra-hot gas giant where things get even weirder. This planet is tidally locked, meaning one side always faces its star while the other remains in darkness. The day side is so hot, over 4,000 degrees Fahrenheit, that iron actually turns into vapor. It rises into the atmosphere, moves toward the cooler night side, and condenses into iron rain. In short, this is a planet where it literally rains molten metal. Even crazier? JWST has found metal clouds on similar exoplanets, made not of water but of vaporized titanium or aluminum oxide. These exotic weather systems are helping us understand how chemistry, physics, and temperature interact in environments beyond anything Earth has ever seen. Not all alien weather is confined to gas giants. Take 55 Cancri, a so-called super-Earth, a rocky planet with extreme conditions. Its surface may be covered in oceans of molten lava due to its close orbit to a bright star. Temperatures fluctuate wildly between the day and night sides, possibly creating lava vapor storms that shift across the surface. or K2141b, where scientists believe rocky particles are vaporized on the hot side, whipped into the sky by winds and rained down as stone on the cold side, creating a literal rock cycle in the atmosphere. These aren't just oddball worlds, they're examples of entirely different climates. And they challenge everything we thought we knew about what a planet can be. You might ask, why study alien weather at all? Because atmosphere equals chemistry equals life potential. By understanding what atmospheres are made of and how they behave, we learn which planets might be habitable, or at least chemically interesting. If a planet has clouds, storms, or even a stable climate, it might have surface conditions that could support life. Even more, these weather systems give us direct insight into the formation of planets, the dynamics of climate, and the interaction between a planet and its star. And someday, these insights will help us interpret data from Earth-like worlds. Final thoughts. The more we learn about exoplanet weather, the more we realize how weird the universe truly is. Our solar system, with its frozen moons, gas giants, and stormy gas bands, is only a tiny slice of what's possible. Beyond it lie worlds with skies full of glass, iron, ash, and molten rock. Storms rage there in silence, driven by physics so extreme they stretch our imagination. These are not just distant curiosities, they're the stepping stones to answering one of the biggest questions in science. What is out there? And could it ever be like here? The discovery of rogue planets floating freely through space. There are planets out there drifting alone through the darkness, untethered to any star. No sunrise, no orbit, no seasons, no parent star to warm them, to anchor them, or even to give them light. Just cold, eternal night. They're called rogue planets, and for a long time they were more theory than reality. A strange idea that worlds could exist outside the gravitational grip of any solar system, like orphans of the cosmos. But in recent years, astronomers have gone from suspecting that rogue planets might exist to finding dozens, possibly hundreds, and now, maybe billions. This is the story of how we discovered these wandering worlds, why they matter, and what they might teach us about the nature of planets, star systems, and maybe even life itself. What is a rogue planet? A rogue planet, sometimes called a free-floating planet, is exactly what it sounds like. A planet that travels through space without orbiting a star. They're not like Pluto, far and cold at the edge of a system. They're not like comets passing in and out of solar influence. Rogue planets are completely unbound. They're not part of a system at all. Instead, they drift through the Milky Way, alone, like ships cast adrift from the fleet. Some may have formed like regular planets around a star and were later kicked out by a gravitational encounter. Others may have never had a star at all, forming in isolation from collapsing clouds of gas that simply never ignited. They're hard to find, very hard. Because unlike stars, they don't shine. They don't emit light, and most are cold, faint, and completely invisible in normal telescopes. But we've started to detect them, and what we're finding is wild. The breakthrough in detection. For most of the 20th century, rogue planets were just a hypothesis. Scientists assumed that some planets must be ejected from young star systems during chaotic formation stages. But there was no way to prove it. That changed with the development of a technique called gravitational microlensing. Here's how it works. When a massive object like a planet passes in front of a distant background star, its gravity bends the light from that star. It acts like a magnifying glass. The background star briefly gets brighter, not because it changed, but because its light was bent around the object in front of it. That lensing event only lasts days or even hours. But if you see one and no light from the foreground object is detected, that's a clue. You may have just spotted a rogue planet, dark, silent, invisible, but still bending light. Microlensing doesn't require the planet to emit light. It only requires gravity, and every planet has gravity. Surveys like MOA, Microlensing Observations in Astrophysics, and OGLE, Optical Gravitational Lensing Experiment, started watching tens of millions of stars constantly, and after years of patient observation, they began to see the unmistakable signals, sudden brightening of background stars with no visible source, planet-sized lenses again and again. This wasn't just a few rare objects, it was a pattern, and the implication was shocking, a galaxy full of wanderers. The data suggested something bold. There could be as many rogue planets as there are stars in the Milky Way, or even more. Billions of planets wandering in darkness, some as massive as Jupiter. Some possibly the size of Earth. Some rogue planets may have once been part of multi-planet systems where gravitational instability flung them out. Others could have been torn away by nearby stars passing through the system. And some may have formed in isolation, like failed stars that never ignited into nuclear fusion. But whatever their origins, one thing is now clear. Rogue planets are common, and with new instruments coming online, including the Roman Space Telescope, we're about to discover a lot more. What could these worlds be like? So what's it like on a rogue planet? At first glance, it sounds bleak. No sun, no warmth, no day or night cycle, just permanent cold. But don't count them out. Some massive rogue planets might retain internal heat, left over from their formation or from radioactive decay in their cores. That heat could be trapped by thick atmospheres, possibly making the surface warmer than expected. Even more intriguing, if these planets have subsurface oceans like Europa or Enceladus in our own solar system, they might maintain liquid water beneath icy crusts, even in the absence of a star. In other words, rogue planets could be habitable, at least in theory. They might not support life as we know it on the surface, but deep inside, under ice and rock, with the right chemistry, it's not impossible. And that changes the way we think about the universe, because for decades we assumed life needed a stable star and a cozy orbit, like Earth has. But if life can persist on rogue planets too, that means there could be far more opportunities for it to arise, not just billions of Earth-like planets orbiting stars, but also billions of lonely worlds in the dark, each with its own story, its own heat, its own chemistry, and maybe even its own life. Science fiction becoming science fact. Rogue planets have been a staple of science fiction for years. In stories, they're mysterious haunted places, settings for lost civilizations, alien labs, drifting doomsday machines, or even planets that get captured by new stars. And now we know they're real. We've already begun identifying them, and we've barely scratched the surface. Imagine a future where interstellar probes explore not just stars, but the space between them, navigating through cold gravitational deserts, pinging signals off of dark worlds no one has ever seen. A quiet form of exploration, but one with massive potential. Rogue planets could also be stepping stones for future space travel, offering gravitational boosts or refueling stops for deep space missions. In time, they may become important waypoints in the interstellar frontier, and who knows what secrets they might hold. Final thoughts. We like to think of planets as things that belong to stars, as parts of a system, a family, but nature isn't always so neat. Some planets are cast out, some are born alone, and some choose isolation in ways we're only beginning to understand. What we once thought were rare cosmic flukes are now emerging as a common feature of the galaxy. Wandering worlds are out there, in the billions, dark, cold, and quiet, but very real. They remind us that the universe is more chaotic, more unpredictable, and more full of mystery than we ever imagined. They're out there right now, floating between the stars, waiting to be found. And one day we just might visit. Black hole jets are weirder than we thought. Black holes are known for pulling things in, not spitting them out. But some of the most powerful phenomena in the universe come not from what black holes consume, but from what they eject. For years, astronomers have observed black hole jets, long beams of high-energy particles that shoot out from the regions around spinning black holes at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, and they're so bright we can see them from across the universe. But now, we've seen something new. A recent observation caught a spiral-shaped jet, twisting through space in a corkscrew pattern, something never captured in such detail before. And it's rewriting how we think black hole jets actually work. What are black hole jets? Let's start with the basics. At the center of most galaxies, and including our own, is a supermassive black hole. These black holes feed on gas, dust, and sometimes even stars that get too close. As matter spirals into a black hole, it forms a spinning, superheated disk. And from that disk, under the right conditions, twin jets can erupt from the black hole's poles, blasting out particles at near light speed. But here's the thing. Black holes don't shoot jets directly. The jets are formed from the magnetic chaos in the disk of material around them. And the exact mechanism is still not fully understood. The new discovery in 2024, astronomers using the Very Long Baseline Array observed a distant galaxy with an active black hole. But instead of seeing the typical straight-line jet, they noticed something strange. The jet spiraled outward like a twisting corkscrew. This wasn't an illusion. The jet really was moving in a spiral, not just in shape, but in motion. This behavior suggests the jet is being wobbled or precessed over time, possibly by the spin of the black hole itself, or by the gravitational tug of another massive object nearby. It's like watching a fire hose flail in slow motion across light years of space. Why this matters? This spiral pattern gives us clues about what's happening near the black hole's event horizon. It tells us about the orientation and spin of the black hole, the magnetic fields involved, and even the possibility of binary black holes, which could explain the wobbling. It also challenges models that assume jets are rigid and straight. Instead, this new data suggests they might be dynamic, flexible, and shaped by much more complex forces. Final thoughts. A black hole jet in the shape of a spiral might not seem like a big deal at first, but in astrophysics, shape means physics, motion means energy, and structure means understanding. The more we study these jets, the more we learn not just about black holes, but about how galaxies grow, evolve, and influence the universe around them. We thought black holes were all about gravity and darkness. But it turns out they also paint cosmic spirals of light across millions of light years. And now we finally know how to see them. Entangled particles and the strangest experiment in space. Imagine two particles, maybe photons, maybe electrons, created together then separated by millions of kilometers. One is sent left, the other right. And when we measure the first, the second seems to know instantly what happened, no matter how far away it is. That's quantum entanglement. A phenomenon Albert Einstein once dismissed as spooky action at a distance. But it's real. It's measurable. And now, scientists are not just studying it in labs. They're testing it in space. In the last few years, experiments have confirmed that entangled particles can remain connected across vast distances, and new tests are being carried out from low Earth orbit, with satellites firing quantum signals to ground stations. This isn't science fiction anymore. It's the cutting edge of quantum physics, space science, and even the early foundation of a future quantum internet. Let's explore what entanglement really is, how it's been tested, and why the cosmos is becoming the next great quantum laboratory. What is quantum entanglement? To understand why this is so revolutionary, we need to go back to the basics. In quantum physics, particles don't have fixed states until they're measured. Instead, they exist in a superposition, a range of possible states. When you measure a particle, you force it to collapse into one outcome. But with entangled particles, things get weirder. These particles share a quantum state. When you measure one, the state of the other is instantly determined, no matter how far apart they are. For example, imagine two entangled photons. One is polarized vertically, the other horizontally. But which is which isn't known until one is measured. As soon as you check the first, the second instantly knows what state to take and will always match the prediction. This isn't just theory. It's been tested again and again. But Einstein hated it. He believed this violated a fundamental rule: locality. The idea that objects are only influenced by their immediate surroundings and nothing travels faster than light. If entanglement is real, something must be happening faster than light. Right? Einstein believed there must be hidden variables. Information we just hadn't discovered yet. Something classical, something local. But in 1964, physicist John Bell devised a way to test this. And over the decades, experiment after experiment has confirmed Einstein was wrong. Entanglement is real. It's not local. And now, we're testing it in orbit. Entanglement on Earth. The first experiments. In the 1980s and 1990s, scientists in Europe and the US built increasingly precise experiments to test Bell's theorem. They created entangled photons using lasers and crystals, then sent them through optical fibers to detectors placed kilometers apart. When one photon was measured, the other's state was instantly known, and always in agreement with the predictions of quantum mechanics. The statistical data ruled out hidden variables. This wasn't a fluke, it was real. But there were always tiny loopholes, places where something classical could still sneak in. Perhaps the detectors weren't truly isolated, or maybe the measurements were influenced in some subtle, undetected way. To truly close these loopholes, you'd need to create space between the detectors. Real distance, real isolation. In other words, you'd need space. The Michus satellite, quantum in orbit. In 2016, China launched a small satellite called Michus, named after an ancient Chinese philosopher and scientist. Michus was no ordinary satellite. It was the world's first quantum communication satellite designed to test entanglement in orbit and beam entangled particles between space and Earth. The plan was ambitious. Create pairs of entangled photons on board the satellite, then beam them to two ground stations over 1,200 kilometers apart, measure the photons simultaneously and see if entanglement still holds. If it worked, it would be the longest distance entanglement test ever performed, and it did work, repeatedly. Michus achieved quantum entanglement between particles over 1,200 kilometers apart, with no classical connection. The results upheld the predictions of quantum mechanics and smashed any remaining doubts that distance could somehow break entanglement. This was more than a physics experiment. It was a proof of concept for something even bigger. Quantum communication. A new kind of internet quantum entanglement isn't just spooky, it's useful. In quantum communication, the laws of physics guarantee security. Any attempt to eavesdrop on an entangled particle pair breaks the entanglement and can be instantly detected. It's unhackable by design. This makes it ideal for secure messaging, encryption, and high-stakes information transfer. The dream is to build a quantum internet, a global network using entangled particles to send data instantly and securely. But regular fiber optic cables have a limit. After a few hundred kilometers, the signal decays. Quantum signals can't be copied or boosted like classical ones. So how do you scale up? With satellites. Space-based entanglement sidesteps the distance problem. Satellites like Michus can act as quantum repeaters, linking distant ground stations across continents. Several countries, including China, the US, Canada, and members of the EU, are now building their own quantum satellite programs. In the next decade, we may see the first generation of global space-based quantum networks. The deeper implications. The fact that entanglement works, not just in labs but across thousands of kilometers of space, tells us something profound about the universe. It means that quantum mechanics holds true everywhere. It's not just a strange behavior of tiny particles in controlled experiments. It's a fundamental property of reality. It also suggests that the fabric of space-time might be more deeply connected than we ever imagined. Some physicists even speculate that space itself might emerge from entanglement, that the geometry of the universe is built on quantum connections. That's a radical idea. But as quantum physics moves beyond the lab and into the cosmos, these aren't just thought experiments anymore. They're measurable, testable, real. Final thoughts. Quantum entanglement once seemed like a ghost in the machine, a mathematical trick with no real-world consequences. Now it's being tested from orbit. It's becoming the backbone of next-generation communication systems. It's challenging our notions of distance, information, and the very structure of space. And it's turning Einstein's spooky action into a practical tool, one that works from thousands of kilometers away, between Earth and sky. In the future, your secure messages, your digital identity, your most sensitive data, all may rely on particles that are entangled and beamed from orbit. And those particles, in their silent, invisible connection, are telling us something deep. that no matter how far apart we seem, the universe might be more entangled than we think.